let's look into the locking operation. The code given below is a simple representation of a concurrency control mechanism to ensure that only one process or a transaction can access the specific resource called as item X. We are in the code checking that if the item is already locked, wait until it becomes unlocked. This will help us to ensure that multiple processes don't access the item at the same time and potentially may cause or potentially cause conflicts or inconsistency. Let us see how it works. The block says that if the item X is equal to 0, it means the item X is unlocked. Now, before start to performing on it, the process has to lock it. So it will keep the value 1 inside the lock to say that the item is locked. Now, if this is not the case, which means that item is locked already. So the operation or the process has to come to the else part and then keep on waiting until the item X becomes lockless, which means it is unlocked and ready to be used. And the lock manager wakes up the transaction to work on it. If this waiting is the case, okay, so you're going to wait and then we're going to go back to the block B. After this wait ends, we check and then we start working on it. This is a simple lock operation. Now let's see how to unlock. Putting a value 0 inside a lock variable on item X makes it unlock. So if you want to unlock, if you have already locked the item X using these two statements, it means you're putting the value, you found that the item X was unlocked, you kept the value 1 inside it, and you started working on it. After you finished working, you want to unlock, so you're keeping the value 0 inside the item X. If any transactions are waiting, then wake up one of the transactions to work on it. So this is how the simple unlock operation is performed. Let's see how the read lock is performed, or how the read operation is performed after locking an item X. We begin by checking if the lock on item X is unlocked, then we start locking it by putting read lock inside it and then incrementing the value of item X read variable to 1. You remember, multiple processes can read at the same time by putting the read lock on it. So you are saying that if the item is unlocked, okay, put a read lock and then increment the counter of the read lock by 1. End it. Okay, so this is the case if it is unlocked. Else we come to the else part, which means that if the item is locked already, what you do? You just increment the counter by 1 again. If it is unlocked, you are putting 1 and putting the read lock and then starting to work. Else, it means that if item was already locked, so now your process is going to increment the read lock by 1. Okay, now else, if this is not possible, okay, because when the item X, what could be the case in which this is also not possible? It means that the item X is locked by a write operation, then you cannot perform it. So what you have to do, you have to wait until lock X becomes unlocked and the lock manager wakes up the transaction to work on it. And after doing this, we again go to block B and check this condition or check this condition to work on. Now let's see how to put a write. Now let us check how to put the write operation. If the lock of X is unlocked, then it is indicating that the item is free. Now we need to proceed to lock the item by putting a write lock inside it and initializing the read counter to 1. This is a simple case. If the item is unlocked, lock it. Else, if the lock of X is already occupied or already under a write lock by another transaction, then read the increment. If both of them are not true, we go to the else part. In the else part, if the lock of x is, you're going to wait. In the third part, you're going to wait until the lock of x becomes unlocked and the lock manager wakes up the transaction. After doing this, we again go back to the block B and check the conditions. So this is the code to perform the write operation. How to remove the write lock? Let us see now. If the lock of x is holding a write lock, if the item x is holding a write lock on it, then unlock it. Wake one of the transactions to work on it. Okay, waking up the transaction which is waiting for item x access, we can wake up it and it can start working. Else, if it is in the read lock, then we are going to subtract the counter by 1 and keep on removing it until it becomes 0. Okay, then once the lock of x is holding unlock, it means it is available for any other transaction. So the scheduler can wake up one of the transactions if it is waiting for item x to be accessed. So we have seen a lock operation, simple lock operation, simple unlock operation, simple read operation, simple write operation, and performing unlock on write operation. Lock conversions. Lock conversions can be done for changing a read lock to the write lock or changing the write lock to the read lock. If we are upgrading the read lock to the write lock, it means we are making the lock more stronger, because a read lock can be shared, but write lock cannot be shared. So we upgrade the lock. Lock item is upgraded. If TJ has a read lock and TI has a read lock and TJ has no read lock, then I is not equal to J. Then convert the read lock X to the write lock X. Else force Ti to wait until the transaction 2 or the TJ unlocks the X. So this is called as lock upgrading. Changing the lock type from read lock to the write lock. How do we do that? If transaction 1 has a read lock and transaction T2 has no read lock, okay, so T1 is not equal to T2, for example, then convert read lock to the write lock. Okay, for example, here it's like T1 is reading, T2 wants to upgrade it for the write lock. So we check here that T1 is having read and T2 is not having read lock, right? T2 is not having, T2 is not sharing the lock with it. It means it wants to write. T2 wants to write. So we convert the read lock to the write lock. Else, we can force T1 to wait until TJ unlocks the X. Okay, now downgrading. Locks can be downgraded by converting a write lock to the read lock. Now here we have a T1, for example, Ti has a write lock on X. It means no other transactions can have any more locks on write. So converting the write lock of X to the read lock of X so that other transactions can use it. So in one conversion, we are upgrading the lock from the read lock to more stronger write lock. In another downgrading, we are downgrading the read lock to the write lock. Two phases. Now, what are the two phases of locking? Locking can grow or locking can shrink. Locking can grow. If you see in the graph, locking is growing or locking is sharing. Okay. So when the graph is going upwards, it means you are obtaining more locks. When the graph is going down, it means you are releasing locks. So begin and keep on growing. It means you are taking more number of locks. Okay. And this is the lock point. And when they are dropping, it means you are releasing the locks. Okay. Over the transaction duration. Hence, the two phases of locking includes a growing phase and a shrinking phase. What is a growing phase? Locking or growing phase is allowing a transaction to apply locks, read or write on a desired item one at a time. Unlocking, a transaction unlocks its locked data items one at a time. So a transaction is like the transaction is like T1 is locking X, okay, and then locking Y, and then locking Z. It is, acquiring more locks on desired data items. You have different data items. This is called as growing phase. Unlocking is releasing phase. What are the requirements for a transaction? These two phases must be mutually exclusive. What is the requirement? It means they should be mutual exclusion. Means if one transaction is, if one data item is releasing if more for a transaction, these two phases must be mutually exclusive. It means it can grow or it can shrink at a given point of time, but not doing both the things at the same time. That is, during locking phase, unlocking phase must not stop, must not start, and during unlocking phase, locking must not begin. So this is the mutual exclusion of growing and shrinking phases of two-phase locking. Now, let us try to understand two-phase locking techniques with an algorithm and their result. You have, there's a transaction T1, there is a transaction T2, and then X and Y have their initial values. X is 20 initially and Y is 30. So Y is 30 here. Y is again 30 here because they just read, T1 just read. Y is 30 here, and then write lock on X. Okay, X is how much? 20. Read 20. Now, what is the value of X? X is equal to X plus Y. So 20 plus 30, X becomes 50. If the transaction T1 executes first, X is equal to 20. Okay. And then what are we doing? We are writing item X. X 20 plus 30, X becomes 50. Sorry, X becomes 50 for the first time. And then we write this item X50 into the disk, and then we unlock X. Okay, so this is how the transaction locks an item, then reads it, then unlocks it, then acquires a write lock on X, then reads the value of X, and then changes the value of X to be X plus Y, which is 20 plus 30, and it becomes X becomes 50. And then we write the value of X50, and then we unlock X. So now here, after unlocking X, it means the data item X with value 50 is available into the database. Now, let us see how the T2 works. Read the, apply the data log. So when now the transaction 2 starts, it acquires a read log on X. T1 made the value of X as 50. So we are going to use 50 here. So T2 will read the item as 50. It will unlock it, obtains a write log on Y to change the value of Y. Y is how much? 30. Okay, here we did not change Y. So Y is 30. And then it says, make the Y as 50 plus 30. So Y becomes 80. Write the item into write the value, update the value of Y as 80 and unlock it. So now if the T1 have executed first and the T2 followed the execution, then the value of X is equal to 50 and the value of Y is equal to 80. Okay, so this is the serial execution, T1 followed by T2. If the T2 executes first, okay, and T1 executes later, then the value of X will become 70 and Y will become 50. So this example is just trying to convey that when you are accessing a data item y, okay, you apply a read lock. Okay, after reading, you unlock it. So this is the operations here. This is the operations here. Let me take a pointer. So this is important. Read lock and unlock. And then apply write lock. Make the changes, write the item, and apply unlock. You can execute T1 first, then T2. Okay, if we are executing T1, we see X as 50, Y as 80. If T2 executes first, it also does the same thing. Apply the read lock, read, and unlock. Apply the write lock, read the item, make the changes, write the item, and then unlock. So if T2 executes first, the initial value will be 30. Here it will be 30. And then, here it will be 30. And then we say write lock of Y. So Y becomes, Y is locked. And then here you say X plus Y. Using the initial values 20 and 30, it becomes Y becomes 50. So we have Y as 50. Y as 50, and then unlock it, and then execute T1. So Y here will be 50. Here we have Y as 50. Y is 50 here. And then you are adding 20 to it. So it becomes 70. And then you are applying these logs before and after accessing it. Okay. So done with this. Okay, next slide. Two-phase locking technique. This one was applying the two-phase locking with serial execution. Okay, now let us see how to apply the two-phase locking with non-serializable execution. Okay, so non-serializable, because you see here, what are we doing? We are reading, we are putting a read lock on Y, then we are reading the item, then we are unlocking it. In the meanwhile, transaction 2 starts, it reads the lock, it puts a read lock on X and reads the item X and then unlocks X, and then write lock, puts the write lock on Y, because the Y has just released its lock, so the T2 is putting a Y lock on it, and then read the item Y. So initially it was okay, so reading the item, and then you remember the initial value of X and Y, they were 20 and 30. So here Y is equal to 20 plus 30, and then write the item Y. So 50 for Y and unlock Y. Then write lock obtained on X, because X is unlocked, so T1 can acquire a write lock on X. Does a read operation on X. X is equal to X plus Y. X plus Y is how much? Y is 50. We just made a Y as 50. Okay, and X was 20. Yeah, X was 20. Now let us discuss the two different algorithms of obtaining a two-phase lock. The first algorithm says that a two-phase locking be applied in a basic way. The other one is a conservative way. Now, what is the basic way of applying the two-phase locks? The basic says that the transaction locks data items incrementally. As in one, they want to use X and Y, they keep on applying the locks incrementally. But this may cause a deadlock, which has to be again handled. Conservative approach of two-phase locking says that approach of two-phase locking says that we have to avoid or prevent the deadlock by locking all desired item even before the transaction begins its execution. This is conservative approach and this is the basic approach. Now, strict two-phase locking says that a more stricter version of the basic algorithm where unlocking is performed after a transaction terminates, either by committing or aborting or rollbacking. This is the most commonly used two-phase locking algorithm. There are two approaches. One is using basic and one is using conservative. Conservative says that lock all the data items even before the transaction begins. Basic says that keep on obtaining the logs on the data item as and when required in an incremental fashion. But this may cause a deadlock to happen. We will see an example how this deadlock happens. And then it has to be handled in different ways. We will see the different ways of handling the deadlock. The strict version is a more strong version on the basic lock, which says that unlocking is performed after transaction is terminated either successfully or by aborting. So the strict two-phase locking, strict 2PL, is the most commonly used one. Now let us see how a deadlock can happen when the transaction T dash and T2 dash is trying to use X and Y by using one of the approach that we discussed just now. T1 is locking the data item Y by applying a read lock and then reading the item Y. Concurrently, T2 applies a read lock on X and a read and it tries to read the item Y. Here, the T1 tries to apply a write lock on X, okay, and wait for X. And here, the T2 applies for a write lock on Y, and you see the write lock of Y is with T1. And the Y is locked by T1 in the read lock, and write lock T1 is applying, but it is held by a read lock by T2. So here T1 has locked X, okay, and T1 is waiting for write lock so that when T2 finish, it can apply write on X. Here is the other situation for Y is similar at the T1. T1 is holding the read lock for Y and T2 is trying to get the write lock on Y. So T1 is waiting for X to apply the write lock and T2 is holding it. T2 is waiting for applying the write lock for Y and T1 is holding it with the read lock. So they are waiting for each other and they can go in a deadlock. T1 cannot finish until T2 finish. T2 cannot finish until T1 finish. As a result, both of them are waiting for each other. T1 and T2 are following the two-phase locking. Okay, but they are getting into the deadlock. Now, there are different ways in which deadlock can be handled. The first one is to avoid the deadlock. The transaction will lock all the data items before it begins its execution. So if before T1, see, T1 is the first one to start here. So what it will do, T1 will go and lock X and lock Y. And then it will work and finish the work. And then T2, and then after finishing the work, T1 will unlock X and unlock Y. And then T2 can start working on it. So even before the T1 starts, it will lock X and Y so that T2 can never take the lock on Y, lock on X, so that T1 has to wait. So it's like I need to access lab 1 and lab 2. I straightforward before taking the exam, I reserve them for my use, so that other teacher cannot use lab 2 from me. Okay, so we don't have the deadlock problem. Now, the second one is this way of locking prevents the deadlock, since the transaction will never wait for the data item. It will just finish its work and then return the data item by unlocking it. The conservative two-phase locking uses this approach. We saw two approaches, right? Conservative and basic. So the conservative uses this approach of deadlock prevention. However, if we are using a basic approach, this is what can happen. We incrementally lock X, and when we try to lock Y, we first lock initially Y, and then we incrementally lock X. When Y, but as a result, what happened? T2 locked X, and we are not getting X right locked, but so the T1 is not finishing at all. So this is the basic approach. Now, in a basic approach, a deadlock can happen. In this approach, deadlocks are allowed to happen. The scheduler maintains a wait for graph for detecting the cycle. It's like, T1 waiting for T2, T2 waiting for T1. So there is a deadlock here. If the cycle exists, then one transaction involved in the cycle is selected and killed and rolled back. So that, for example, T1 is waiting for T2, T2 is waiting for T1. You roll back T2 and T1 gets both the data items that T1 can finish. Then you can start T2 and T2 can work on it. A wait for graph is created using lock table. Okay, so we maintain a lock table and then we create a wait graph. As soon as a transaction is blocked, it is added to the graph. When a chain like T1 waits for TJ, TJ waits for TK, waits for TI or TJ occurs, then this creates a cycle, and then we handle the cycle by using the rollback approach. Deadlock avoidance. There are many variations of two-phase locking algorithm. Some avoid the deadlocks by letting the cycle to complete, or by using the rollback of one of the transaction involved in the cycle. Or we have weighted wound or wound wait algorithm and wait die algorithm to handle the situation of avoiding the deadlocks by using timestamps to avoid deadlocks by rolling back one of the victim transaction. What do we mean by this? We have transaction T1 waiting for T2, T2 waiting for T1. So we apply either wound wait or wait die algorithm, and one of them is rollbacked. Now let us see what are they later. Starvations. Okay, now what do we mean by starvation? Starvation means the transaction is trying to wait until data item X is released by transaction 2 so that it can, start working on it. But the starvation can happen if the T1 is waiting for Tx forever or for a longer time and T2 is not releasing it. Then the starvation will happen. Starvation means your transactions are becoming hungry for data item to work on it and they're waiting for a very long time. So starvations occur when a particular transaction consistently wait or restarted and never gets a chance to proceed further. Then the transaction is said to be starvating because it is not starting, or it is not, proceeding further, or it is waiting for a long time. In a deadlock resolution, it is possible that some transaction may be, continuously selected as a victim and rolled back. For example, you have T1 and T2. There was a cycle, T1 was waiting for T2, T2 was waiting for T1. So T1 is actually the one which is selected and rolled back every time. The same situation can happen with transaction 3 and transaction 2. And transaction 2 is again selected to roll back and T3 execute. So now here, transaction is, not getting proceeded. It is not running. It is every time picked up as a victim and rolled back. This limitation is inherently possible when we are using priority-based scheduling mechanism. So if T2 is having, for example, a low priority, it will always be rolled back. Another transaction will get the time to run. So in the wound wait scheme, a younger transaction may always be wounded or aborted. For example, here T1 and we have T2. T2 was rolled back in the first case when there was a deadlock between T1 and T2. Now we have T3 and T2 now running together. Okay, so now here T3 is new, T2 is the older one which was already aborted. So which one is having the less wait time? T3 is having the less wait time, so it will be rolled back and the chance is given to T2 to execute. Okay, so the younger transaction may always be wounded or aborted by a long running older transaction which may otherwise create a starvation. Timestamp. We use a variable integer that indicates the age of an operation. A larger timestamp value indicates a more recent event or an operation. Okay, the time stamp based algorithm uses timestamp to realize the execution of concurrent transaction. In timestamp, we use an integer value to indicate the age of a transaction. Okay, so for example, you have a transaction T1, age can be its time, when it was started. A larger timestamp value indicates that the operation or the event is the more recent event. Timestamp based algorithm uses time value to serialize the execution of concurrent access.